We're going to practice this more in a different context because we're going to talk about a different kind of potential energy. Where we want to get to is we want to be able to talk about energy inside objects. And so if you think about the ball spring model of a solid object has lots of atoms vibrating on chemical bonds that we model as springs. So in order to analyze this, we need to talk about potential energy associated with springs. So we're going to go back to the macroscopic world for a minute and just talk about springs. Springs are nice and concrete. So we're going to go through the same argument we went through before, getting potential energies as a function of position. And we're going to, so think about a spring. It's got a relaxed length. If I do work on it by stretching it, I put energy into the system. Where'd it go? Did the kinetic energy of the spring increase? Yeah, there must be some potential energy stored in the spring. So let's see if we can figure out what it is. So let's consider a horizontal mass spring system sliding on a frictionless surface, just so we can actually simplify it by not worrying about gravitational interactions right now. So we're going to call this this axis. We're going to give this axis the name S. This is going to be the stretch axis, and this is S equals 0 here. In which case we can write the S component of the force by the spring on the block. The force in the S direction is minus the spring stiffness times the stretch. Let's see if that works out. If we stretch the spring so it's longer, then S is greater than 0. And that says the S component of the force should be that way, and that's good. If we compress the spring so it's shorter, we have now, so this was S equals 0, so now we have S less than 0. The force is that way, so it looks good. Now remember how we found potential energies functions. We said that the gradient, we have negative du d some spatial thing, in this case S, was equal to the force, which in this case is minus k sub S times S. So what we want to do is take an antiderivative and find a function for the potential energy of a spring. Now obviously these minus signs cancel, so we have du ds is k sub S times S. Right? Okay. So what is the right function? What's the potential energy function for a spring such that this works? So we want some function u of S. So just differentiate and see what you get. Okay. Answer 5. That's correct. We have a half times the spring stiffness times S squared. How do we check this? Take the derivative, see if it works. And then there's this constant term. So that looks like the potential energy we put into a spring. So it says it's the more it's stretched, the greater the potential energy stored in the spring. Okay, that makes sense. The more it's this isn't a spring that compresses well, but if it were. Okay, so let's look. So what does this look like? What does this curve look like? We should be able to plot a potential energy curve. So we'll have the stretch axis. So this axis is energy. This axis is stretch. So what does that curve look like? It's a parabola, isn't it? That's a really funny looking potential energy curve. There's a lot of stuff that's wrong with it. Yeah. Every other potential energy curve we've seen went to zero when the separation was large. And in fact, we think it has to, because when we get these two, the proton and the electron, really far away from each other at rest, the total energy of that system is just the sum of the rest energies. So it doesn't do the right thing when R gets big. Yeah. Okay, so you're worrying about real springs, and that's going to bail us out. So you're definitely on the right track. So there's one other thing that's wrong with this, though. What's the other thing that's wrong? Okay, so you've got the pieces of how to fix it. Another thing that's wrong is that for a bound state, remember that K plus U had to be negative. There aren't any bound states here. So that says we can never have a mass bound, that this isn't possible, this bound state. It's just going to fly off to Alpha Centauri. Okay, so that's not very satisfying, but you picked up two of the big pieces. So one is that for a real spring, you can't stretch it infinitely far. It's going to break. And you also can't compress it infinitely far. The coils are going to jam against each other. And also, there's something about bound states that can bail us out, and it's this constant, which we haven't been paying attention to. So suppose we say instead of this curve, what we've got is this curve where we've got this negative constant, E spring or something. And then let's make the corrections you've suggested. So for a real spring, if you can stretch it so far, and then it's not going to be a spring anymore. You're going to get a wire. All the coils are going to be gone. So, and then it's actually going to break. And then there's going to be no energy. And if you compress it too far, the coils are going to jam into each other, and so that's more like the potential energy curve for a real spring, isn't it? So this parabola, this a half K sub s squared, is what we call the potential energy for an idealized spring. Okay, it's some imaginary spring that we're not really going to find. Nonetheless, we can actually do problems where we look at differences without worrying about this additive constant. Now, where are we going with atoms? Well, it turns out that two atoms connected by a chemical bond look just like two masses on a spring, and so the potential energy curve that you get for two atoms bonded together with a chemical bond, two neutral atoms, looks almost exactly like the graph we've just drawn. So you can't get them too close together because then you're jamming the electron clouds into each other too much. The nuclei get, so it's very steep here. And if you pull it far enough, the bond just breaks. So it does go to zero. But in this region, it's pretty parabolic. And so thinking about this as a half K sub s squared is a good approximation for normal small vibrations of atoms. Okay, so let's do a problem involving spring potential energy, just to work it out. We have a horizontal mass spring sliding on a very low friction surface. The spring stiffness is 3 newtons per meter. The relaxed length of the spring is 25 centimeters. We stick a 50-gram mass on the end. You stretch it and then let it go. So how fast what's the kinetic energy at the moment when the spring goes back to its relaxed length? Okay, that's much less of a distribution than last time. A looks like. So let's see what our energy equation looked like. Presumably it said E final is E initial plus work done by the surroundings. That's our. And so what did we have on the E initial side? So what are the energy terms we had under E initial? Okay, so we have the rest energy of the mass. We're approximating the spring mass as negligible, plus initial kinetic energy, plus initial spring potential energy. And on the final side, we presumably have mc squared plus the final kinetic energy plus the final spring potential energy. But wait a minute. What's our system? What's our system? Well, you can't have potential energy in the ball, so it better be the ball in the spring, huh? Okay, so the system. So aren't there some objects in the surroundings that are exerting forces on the system of the mass plus the spring? Like, yeah, there's a gravitational force, there's a normal force. What about the wall? Is this thing going to oscillate back and forth if there's no wall here? Something's got to hold this in, right? So if we've stretched the spring, what's the direction of the force exerted by the wall? Well, there's a force, isn't there? So if the spring is stretched, the wall must be pulling on it. Well, am I not actually pulling up on this end of the spring? And yeah, so what about this work term? There's external forces. What about the work term? What? Well, there's a force. The wall's definitely exerting a force. Oh, okay. So work, we need an Fx delta x. So Fx is not 0, but what's the displacement of these atoms? 0, essentially, isn't it? Yeah, yeah. So the wall's only able to exert a force on these atoms of the spring, and they're not moving. So this is 0. So the force changes the momentum, but the work is 0. Okay. And the rest energy didn't change. So we have a half mv final squared plus, what's the final spring potential energy? 0. And we have, what was the initial kinetic energy? Okay, this was an easy problem. Plus a half K sub S. And what was the initial stretch here? 0.04. So it's the, remember, stretch is the current length minus the relaxed length. The current length, yes, you're right. So we started out with 0.9, and thank you. All right. So that's the, and so then we solve it and get some number. Probably 1. Was it 1? 1. Okay. So good question. So remember that we said for a real spring that we were going to add this potential energy, this negative constant, so that we could have bound states. So really, we have to add this, we should be adding this into the potential energies here. So we have this negative constant E sub s here, but notice that we've also got it over here. And so it's the same on both sides. And so we often just omit it. It's okay to write it, but we often omit it. All right, let's think very quickly about another problem which is worked out in the book, so you can look at it there. Here's the situation. We have a spring sitting vertically. A block is dropped onto the spring. At the moment we are looking at it, it's got a speed of 2 meters per second down. We want to find, in fact, find the speed of the block just before it hits the spring. What are we going to pick for initial and final states? Okay, but so we know the initial state. We know the final state is just before it hits the spring. The problem asked in the book is the block hits the spring, keeps moving down. At the moment when it's 0.3 meters above the floor, how fast is it moving? What will we take for initial and final states to solve that problem? We could, in fact, just take A and C, because we don't need to know what happened in between. It's only the initial and final states that matter. So we could find how fast it's moving here and then go from there to there, but we don't have to. This is called path independence. Potential energy depends only on position, not on how you got there. So it doesn't matter how you got there. So I suggest that you study that example in the book.